Okay, so basic terminology and concepts. So power. The quantity work has to do with a force causing a displacement. Work has nothing to do with the amount of time that this force acts to cause the displacement. Sometimes the work is done very quickly. I'm just going to make that a smidge bigger for me. Sometimes the work is done very quickly, and other times the work is done rather slowly. For example, a rock climber takes an abnormally long time to elevate her body up a few meters along the side of a cliff. On the other hand, a trail hiker who selects the easier path up the mountain might elevate her body a few meters in a short amount of time. The two people might do the same amount of work, yet the hiker does the work in considerably less time than the rock climber. The quantity which has to do with the rate at which a certain amount of work is done is known as the power. The hiker has a greater power rating than the rock climber. Power is the rate at which work is done. It is the work-time ratio. And mathematically, it's calculated with power equals work over time. Or P equals W over T. Hold hands over the weekend, Joel?
Oh, yeah, there we go. Thank you.
Merry Christmas. They look expensive. No? The standard metric unit of power is the watt. What's happening? I didn't write it. Wasn't me. Named after James Watt. As is implied by the equation for power, a unit of power is equivalent to a unit of work divided by a unit of time. Thus, a watt is equivalent to a joule per second. 1 watt is a joule per second. For historical reasons, the horsepower is occasionally used to describe the power delivered by a machine. 1 horsepower is equivalent to approximately 750 watts. So a watt is a much, much smaller, more precise unit of power. Carter, did you find out what the deal was with the horsepower?
No.
Didn't find it? Most machines are designed and built to do work on objects. All machines are typically described by a power rating. Power rating indicates the rate at which that machine can do work upon other objects. Thus, the power machine is the work-to-time ratio for that particular machine. The car engine is an example of a machine which is given a power rating. Power rating relates to how rapidly the car can accelerate the car. I should mean the engine. Suppose that a 40 horsepower engine could accelerate the car from 0 miles an hour to 60 in 16 seconds. If this were the case, then a car with 4 times the horsepower could do the same amount of work in 1/4 the time. That is to say, a 160 horsepower engine could accelerate the same car from 0 to 60 in 4 seconds. The point is that for the same amount of work, power and time are inversely proportional. The equations can be guides to thinking about the relationships between quantities. And that's a good way to think about things, not just sort of a way to solve problems. The power equation suggests that a more powerful engine can do the same amount of work in less time. So let's just talk about the personal power rating lab where you got to run up the stairs. What kind of people have an advantage? And I'm not saying like kind of people. Like what kind of physical attributes could a person have that would give them a higher power rating? Okay, athletic. What if they're a large, massive person? What do they have to do? They have to run faster, right? If you're really, really small, you don't have to run as fast. But theoretically, you don't have as much strength to get yourself up, right? Generally, to be powerful, you want to be light and athletic and fairly strong, right? Really large people who aren't very athletic and have a hard time expending a lot of power, or a lot of energy, are going to have a tough time. Really, 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 really light people have to run really super fast, right? So there's sort of that trade-off there. One time I had a top 10 power rating for students, and then people tried to beat numbers, but then it kind of got too competitive, and they never stopped running up and down the stairs, so I gave that up. A person is also a machine which has a power rating. Some people are more powerful than others. That is, they are capable of doing the same amount of work in less time or more work in the same amount of time. In the personal power lab, students determine their own personal power by doing work on their bodies to elevate it up a flight of stairs. By measuring the force, displacement, and time, we were able to measure our personal power rating in watts. And then you can convert it to horsepower if you want. Brandon, here's the listening part. Here's where you learn. Joel. Yeah? Go ahead.
1 metric horsepower.
You can put your hand down, yeah.
Okay. 1 metric horsepower is needed to lift 75 kilograms, the average body weight of a person by 1 meter in 1 second.
Right. But why was it called a horsepower originally?
Because
That's what a horse could do?
what a horse could do.
Yeah. Yeah, that's what a horse could do. Okay, so back to our personal power rating lab. Suppose that Ben Pump and Iron elevates his 80 kilogram body up the 2-meter stairwell in 1.8 seconds. If this were the case, then we could calculate Ben's power rating. So this is how you're going to do it tomorrow. It can be assumed that Ben must apply an 800 Newton downward force upon the stairs to elevate his body. How'd they get 800 Newtons? How much does Ben, what's his mass? 80. So they really took 80 times 9.8, which I know is not 800. It's going to be like 780 probably, right? Am I right? They round it up, I guess, or they multiply by 10, yeah. Stick figs or whatever, right? So we got that 780 newtons or 800 newtons downward force. So he has to push up with 800 newtons just to get his body to go up, right? By doing so, the stairs would push upward on Ben's body with just enough force to lift his body up the stairs. It can also be assumed that the angle between the force of the stairs on Ben and Ben's displacement is 0 degrees. Now, that's not entirely true, because when you step up, right, like you're pushing down, but because your leg is at that angle, right, and actually it changes as you go up, right? So there's actually a fair bit of calculus here. The horsepower that we determine tomorrow is in no way accurate whatsoever. I've had really strong guys go up the stairs and they get a horsepower rating of like 1.5 horsepower. There's no way that a 17-year-old person is more than 1 horsepower. They're not as big as a horse, right? But it's got to do with the angle of the knee and on all that, right? Okay, so with these two approximations, Ben's power rating can be determined as shown. So work divided by time. They said that the stairwell was 2 meters tall, so you're going to have to measure how tall the stairs are, right? And he did it in 1.8 seconds, so 800 times 2 divided by 1.8, or 889 watts, which is a little over 1 horsepower. There's no way Ben is more than a horse. They eat more than a horse. The expression for power is work divided by time. Now, since the expression for work is force times displacement, and here's a new formula for you, actually. The expression for power can be rewritten as force multiplied by displacement divided by time, right? So just look at this here. I'm not even going to bother reading that. Power is work over time, and work is FD over T, right? What else do you know is D over T? Velocity, right? So we can say also that power is force multiplied by velocity. That's a new formula for power. I guess that would be, yep. Now, you don't see that very often. They use it in the book examples. You go right ahead and use it if you want. It's useful at times, but it's just another derivation. This new expression for power reveals that a powerful machine is both strong, big force, and fast, big velocity. The powerful car engine is strong and fast. The powerful farm equipment is strong and fast. The powerful weightlifters are strong and fast. The powerful linemen on a football team are strong and fast. A machine which is strong enough to apply a big force to cause a displacement in a small amount of time is a powerful machine. So fast and strong. Okay, so if you flip your page, you should see clicker questions. Am I right? I think I'm going to take a few minutes and talk about number 7 right now. I'm going to take a few minutes to talk about number 7 right now. I already did it with you guys. So. Your household's monthly electric bill is often expressed in kilowatt hours. 1 kilowatt hour is the amount of energy delivered by the flow of 1 kilowatt of electricity for 1 hour. Use conversion factors to show how many joules of energy you get when you buy 1 kilowatt hour of electricity. So 1 watt is 1 joule per second, right? So a kilowatt would be 1,000 watts, which would be 1,000 joules per second. Well, 1 kilowatt hour is 1,000 watts for 1 hour. So if you get 1,000 joules every second for a whole hour, how many joules do you get? That's what they're asking. 1,000 joules every second for a whole hour. Okay, let's see how we did. So yeah, almost everyone got this. 2 physics students, Will and Abel, and Ben pump and iron in the weightlifting room. Will lifts the 100-pound barbell over his head 10 times in a minute. Ben lifts the 100-pound barbell over his head 10 times in 10 seconds. Which student does the most work? They are the same. It doesn't matter how fast you go. Which student delivers the most power? Clearly it is Ben. He's doing it a whole lot faster. Jack and Jill ran up the hill. Jack is twice as massive as Jill, but Jill ascends the same distance in half the time. Who did the most work? Carter, here's the teaching and learning part. Who does the most work? Jack. How come? He's twice as big. They both went up the same height. He has more potential energy because he's more massive. Jack does more work. Who delivered the most power? They're the same. How come? Because Jill did it in half the time. So Jack did twice as much work, but she did it in half the time. So it's the same amount of power. Okay, so that translates to in our lab, Will, that someone who's larger in the class, if they run up in the same amount of time that a smaller person runs up in the time, right? The smaller person is actually going to be more powerful, right? A tired squirrel of mass of 1 kilogram does push-ups by applying a force of 8 center of mass 5 centimeters in order to do a mere 0.5 joules of work. All you have to do here is take the work divided by the time. 0.5 divided by 2. And you get 0.25. 0.25 watts. When doing a chin-up, a physics student lifts their 42-kilogram body a distance of 0.25 meters. Brandon and Will, in 2 seconds, what is the power delivered by the student's biceps to 1 decimal place? So you have to take the weight force, mass times gravity, so 42 times 9.8, whatever that is, right? Actually, we can do it all in one step. So it's going to be work equals the weight force, so 42 times 9.8 times the distance, which is 0.25, all divided by 2, and you should get 51.5.
I put 120 zeros and 36.
This one here would, if you did this, what did you round?
We put 4-5.
Yeah, I did that too.
Right?
I would accept it right on its paper test, but.
Thanks.
So this number here is going to be 1,000 times 3,600, 60 times 60, which is 3600, and then 3 more zeros, which is 3.6 million joules. The escalator one. 20 passengers every minute, which is 60 seconds. From the first floor to the second floor is 5.2 meters, so my distance is 5.2. The average person's mass is 54.9. Determine the power requirement of the escalator in order to move this number of passengers in this amount of time. Round to the nearest whole number. So, first of all, your mass is going to be 20 times 54.9. 98. Like that, Shelby? That's going to be kilograms. And so now power equals work over time. The work is FD over the time. So that's going to be 1,098 times 9.8. Sure, we could do it all in one step. Times that distance of 5.2 all over
1 minute.
60. Oh, I guess I can just look here for an answer, can't I? 933 watts.
Yeah, round it in.
Which really isn't a whole lot. That's like
I didn't round it in.
just over 1 horsepower.
Down to a number.
Saved your life.
Okay. Tomorrow we'll be running up and down the stairs. If you want, I need to do this. In the old days, some of you maybe did the Millikan experiment, the video in grade 11s, but many of you didn't if you had me and Mr. Smigowski second semester, or first semester, I mean. So it was a video version of this lab. We don't have time for that. So anything that pertains to any video, just ignore it. I basically need this handed in, this sheet, okay? By the end of the week. You're going to get time tomorrow to run up and down the stairs. If you want to start it today, you can, actually. So everything you need to fill this all in. There are some post-lab questions on the back. Okay, you should do all of those, and you only need to pick one of the two on the back, either 6 or 7. Only do 6 or 7. Only do one of 6 or 7. You have to do all the other 1 to 5. Right? But you only need to do either 6 or 7.